In our worksheet, we were asked to identify various theories of acids and bases. We have worked with two of those theories so far, the first being the Arrhenius theory of acids and bases, and the second is the Bronsted-Lowry. The first few questions on our homework page ask us to review the Arrhenius definition, knowing that an acid is defined as anything starting with an H, and a base releases an OH, the hydroxide. The first question asks us to identify acids as monoprotic, which means containing one hydrogen ion, diprotic, which means two hydrogen ions, or triprotic, which is three hydrogen ions. We'll write the formula as part of our work, and based on the formula, decide if there's 1, 2, or 3 hydrogens. The term hydrobromic acid, again acid starting with an H carries a +1. Hydro root word ic tells us to write the bromide, HBr. Our formula for hydrobromic acid is simply HBr, and we can see that it would be a monoprotic acid since it contains one hydrogen ion. Sulfurous acid, in our next example, comes from the polyatomic ion sulfite. I look up sulfite, it's SO3 carrying a -2 charge. And when I hook my hydrogen based with a +1, crisscrossing we get H2SO3 is the formula for sulfurous. This then would become a diprotic acid since it contains two hydrogen ions. The third example is listed as acetic acid, which comes from the polyatomic ion acetate, C2H3O2 carrying a -1. The hydrogen we place out front to balance the charge shows C2H3O2 as the formula for acetic acid. It's only the first hydrogen, that is the acid hydrogen. If they appear later in the formula, we've learned that they are not ionizable hydrogens. So even though there's 4 H's in our formula, only one of those is considered an acid hydrogen. It is monoprotic. Phosphoric acid, ic coming from 8. Writing out phosphate, we get PO4, who we know is a -3 charge. Hydrogen with its +1, so when we write its formula, H3PO4. Counting those 3 hydrogens shows us that is a triprotic acid. So with this objective, we're simply writing formulas and counting out how many hydrogens it took to balance the negative ion. The second bullet has us review bases. We recognize that an Arrhenius base ends with a hydroxide ion, the OH -1. We can produce an Arrhenius base from an active metal in water. For example, when lithium metal reacts with water, lithium is written as Li, and the reacts with is the plus sign. I often like to write water in these single replacement reactions as HOH, and I can recognize now that the first name, hydrogen ion, is the acid ion, and OH negative is the base ion hydroxide. So in our single replacement reaction, lithium kicks out the hydrogen and generates H2 gas, leaving us with the Arrhenius base, lithium hydroxide, LiOH. And based on charge, we need just one of those ions apiece. We do need to balance. Since I have 2 H's from the hydrogen gas, we'll double the water, which makes me then double the lithium hydroxide base. And again, going back to repair the lithium, we end up with a 2 to 2 to 1 to 2 stoichiometric ratio. When a metal, active enough to displace hydrogen from water, reacts to produce an Arrhenius base, it's simply a single replacement pattern. The next example asks us to consider barium placed in with water. Thinking of water in terms of its acid and base, hydrogen ions and hydroxide ions, we can see the pattern of single displacement, where barium displaces hydrogen, leaving us with the Arrhenius base, known as barium hydroxide. And based on charge, we get a +2 hooking to a -1. We would write that as BaOH taken twice. This equation has 2 OHs, 2 H's, so we'll need to double the water to balance that out. A 1, 2, 1, 1 balances that equation. So the first of our two working definitions of acids and bases considered Arrhenius. Acids start with H. They are considered mono, di, or triprotic depending on how many H's start their formula. And bases end with OH, the hydroxide ion. The second of our definition broadens that to consider other examples of acids and bases. Sometimes acids don't necessarily start with an H and bases don't necessarily have to end with an OH. The better working definition is known as the Bronsted-Lowry Definition. It defines an acid to be a proton donor. Another name for a proton, recall, is a hydrogen ion. A base, then, therefore, is a proton acceptor. Remember, it could also be called a hydrogen ion acceptor, that an H plus and a proton are interchangeable. So acids donate their protons and bases accept those protons. And with the Bronsted-Lowry acid-base theory, we talk about conjugate pairs. For every acid, we have a conjugate base, and for every base, we have a conjugate acid. Conjugates simply differ by one hydrogen ion. So if I have a conjugate, they are only different in their formula by one hydrogen ion. And I remember the acid always has one more hydrogen. So some good notes there on the side. In the next example, we're being asked to write conjugate acids for the following base. So keep in mind, we are looking at a list of bases and want to write its conjugate acid. For each one of these, to turn the base into an acid, we add one proton, add a hydrogen ion, and remember to consider the charge. When I add one more hydrogen ion, it becomes one more positive on the number line. For instance, here's a base known as ammonia, NH3. When I add another hydrogen, we had 3, adding one more gives 4. It started neutral, and becoming one more positive on the number line gives it a net charge of +1. The conjugate acid for ammonia is the ammonium polyatomic ion, NH4 with a +1 charge. In our second example, HCO3 -1. This is known as the hydrogen carbonate or the bicarbonate polyatomic ion. It's acting as a base. To turn it into an acid, we add one more hydrogen, and when we do so, we become one more positive on the number line. So adding one more gives us H2CO3, and the -1 now moves up 1 unit on the number line to give us a neutral charge of 0. H2CO3 is the conjugate acid for the bicarbonate ion. The third example is carbonate, CO3 -2. Adding a single hydrogen, moving 1 up on the number line, gives us HCO3 -1. OH negative is called hydroxide. Adding one more hydrogen creates a neutral water molecule. And water, if it gains one more proton, forms the hydronium, the acid ion found in water. Each time when we add one more hydrogen, make it become one more positive on the number line. And in the next series of examples, it's going the opposite direction. If we're to write conjugate bases for the following acids, we remove a proton. And when we remove a proton, it becomes one more negative on the number line. So for instance, with HCl, if I remove the hydrogen, it turns into the chloride ion, Cl carrying a -1 charge. This example, this should be a big S, HSO4 -1, superscripted there. Taking off that hydrogen gives us a sulfate -2. So HSO4 -1 loses a hydrogen and becomes one more negative, forming sulfate. H2SO4, removing a single proton, conjugates only differ by one hydrogen ion, gives us HSO4 -1. Same idea with the dihydrogen phosphate ion, leaves us with one hydrogen left, HPO4, and the -1 goes down 1 unit on the number line to a -2. The next example is water. When water loses a proton, it becomes the conjugate base hydroxide, OH -1. And the acid proton hydronium, H3O+, loses its extra proton to go back to the original molecule of water. So, with the conjugate pairs, the acid has one more hydrogen, making it become one more positive, and the base becomes one more negative when we remove the proton. Sometimes we're being asked to actually create the conjugate pairs. In the next example, we're being asked to consider the ionization of hydrogen sulfate ion in water. We'll begin by writing that polyatomic ion, hydrogen sulfate. Its formula, right off your polyatomic chart, HSO4 -1. And if we place that into water, we set up an equilibrium in which we can exchange the proton. Now in this example, it's acting as an